Hi guys, good morning. Welcome back to the new video. In this video, we're going to see problem number of ways to reorder array to get same BST. But before that, a quick rant. Corporate life sucks. Legit. Not going too deep, but yeah. Firstly, in this video, we're going to see great combinations of 2-3 things. Firstly, if you want to know the intuition entirely, so please skip the next 10 seconds because I'm going to name those things. But yeah. What we're going to see is a combination of maths, combinatorics. DP is very less used, like legit negligible, but recursion. So combinatorics plus recursion is the prime thing for this. Okay, cool. Let's quickly jump onto the problem. Number of ways to reorder array to get the same BST. And the problem itself says that okay, we have an array, we have to reorder the array, we have to know the number of ways to reorder the array, and what's the aim like? The aim is to get the same BST, which means this array, whatsoever BST is having, we have to get the same BST of any other ordering which we make out of this particular array. It is the statement itself. The only thing which is not in this line which I have told is that we have an array nums, which is the permutation of numbers from 1 to n. When we say permutation, it is just unique numbers 1 2 3 4 5 6 7 up till n, and those can be in any order whatsoever. And just it is saying okay, what is a BST like? If you don't know, a BST is if you have a 2, the smaller element comes on the left side of that element and the bigger element comes on the right side of that element. Cool. Let's say in this example 2 1 3, so 2 will come first because see, I have to go in from left to right in the array. Okay, I got a 2, I have to place a 2. Then I got a 1, I have to place a 1. And that can only be placed in the left of 2. I got a 3, that can be placed in the right of 2. Cool. If we have to make a BST, and see, the BST for this was made as 2 1 3. The BST of this will be made as 2 3 1. You see, it looks exactly same. Yeah, that's the reason. For this, the BST will be made as 3. It came in first, so it will be placed in first. Then a 2 came in. Then a 1 came in. So as soon as the number is coming in, we are placing that in the tree, and that is how you saw that the BST of 3 to 1 will make something like this. Cool. We have to find the number of ways to reorder nums such that the BST form is same and that the answer can be pretty large. So printf modulo 190%, which is the prime number. Cool. This example we saw just above that okay, we have this input as 2 1 3 for sure. If we have to make a same BST as this, so the only other option is 2 3 and 1, which means 2 3 and 1. Now see, in these kinds of examples now, you have to build kind of a logic, and the intuition can be only be grasped from the example itself. So example helps in these problems to make okay, what is the pattern like? In these problems, you have to figure out the pattern, and that pattern, it's not the standard tree pattern or like this pattern, but yeah, how that is being built, how the example is being built. So if we just see, we are only using the examples itself, no other funky stuff, no other big stuff we are using. So as I look at this example 2 1 3, the problem itself stated that okay, the other ordering can be 2 3 1. Now the first thing which I'm curious of, okay, what is the other ordering possible? Here the one ordering is 2 1 3, 2 3 1. What is the other ordering possible? Other ordering can be 1 2 3, 1 3 2, 3 2 1, 3 1 3, 3 1 2, and so on and so forth. And this 2 1 3 and 2 3 1. Now, why these are not the answers? Let's see. If I had placed 1 in the beginning, which means I'm taking this, let's say, if I've placed 1, then next time I'm going to place either 2 or a 3. If I placed a 2, that will come here. If I placed a 3, that will come here. If I placed a 3, that will come here. If I placed a 2, that will come here. Do you remember one thing? The root was 2. The root is here 1, root is here 1 in these examples. If I had taken this, the root would have been 3 and it would have been 2 and 1. By this, it would have been 3 1. Sorry, it is left side. 3 2 and 1. In this, it would be 3 1 and 2. Here also the root is 3. Root is 3. One thing for sure. See, I'm not doing anything. I'm just saying, okay, I saw the example itself and I saw, okay, it is the answer. Why is others not the answer? Why? What's such a difference in them? Can I figure out some pattern out of it? That okay, it is not the answer, it is the case. That is, I'm trying to figure out. Okay, I saw that it is not the answer because for sure I wanted my 2 as the root, and I could see if I just build this also, so it will look 2 3 1 3. So for sure 2 is the root, but if I place any other element in the beginning, so it will come as the root, it will come as the root, it will come as the root, it will come as the root. So for sure I cannot start with 1 or 3. So the only option remained for me was to start with 2 itself, right? To start with 2 itself, and thus I started with 2. Now as I started with 2, as it said, okay, you can either place a 1 or a 3. I placed a 1 in the beginning here. Other option was I can place a 3 here. That's the reason it came as 2. Okay, from this I got to know, okay, I have to place the root as the same element I want right now as my root. Now let's go on to the next example. Okay, from my example I got some information out, not the entire one. I cannot find all the number of ways. I could only find, okay, it should be a root, and it's looking like a root. Okay, cool. So root should be exactly same, and rest maybe it is 1, it is 3, it is 3, it is 1. It is 2 ways, but cannot figure out the exact formula and stuff. So yeah, let's go on to the next example, which is the bigger example, because bigger example help us to figure out what is a pattern like. Now 3, see, firstly input is 3 4 5 1 2. If I just make tree randomly from myself, not looking at this, from myself, from this array, it will be 3 came in, then the 4 came in, then the 5 came in, then the 1 came in, and then the 2 came in. Cool. And where say came in, I will just place, okay, if that 4 came in, it is more than 3, so please place it after 3. If that 5 came in, so please, the tree right now made is 3 and 4, just place a 5. As 1 came in, okay, 1 will be a left of 3 because it is smaller than 3, so I will just place a 1 here. Now 2 came in, as 2 came in, it is left of 3 but more than 1. Simply I'm just making a BST, and that is how, okay, I can build a BST out of my array. Now comes the interesting part. One thing from above example you for sure know that, okay, you have to reorder these 5 elements, right? One thing for sure, you know that 3 will for sure be placed first because it is the root, and for sure if it is the root, then one thing, it will be placed first. So 3 is always fixed, and you will see the same stuff. 3 is always fixed. Great, one thing I solved. 3 will always be fixed. Now come the chance to place these remaining 4 numbers on these 4 places, because ultimately I want the reordering. I want, okay, what all possible conditions are there. Now let's quickly jump. Let's see. Okay, we have these as examples. If at next place I'm gonna place a 1, can I place it? Now we will try to actually neglify or basically reverse or contradict our answer. 3 is here. I have to place a 4. Okay, it can be chance I can place a 4 here. I can place a 4 here. Anyways, I can just place a 4. After that I'm placing a 5. Remember, I placed a 4, after that I'm placing a 5. What if I had placed a 5 and after that a 4? What's the change? What's the change? That is one thing. Okay, if I'm placing a 4, I don't know what's the ordering, but I just want to know, okay, I'm placing a 4, after that I'm placing a 5. That's the reason it is coming like this. Else it would be like this and this. I am placing a 4 and then a 5. Placing a 4 and then a 5, it is coming like this. If I had placed a 5, then a 4 would come like something like this. So one thing for sure, okay, ordering on the right part is also important. That I need to make sure, okay, if the 4 is coming in, after that the 5 is coming in. Because 3 I have fixed. Now I have the remaining right part to order, remaining the left part to order, and also the left-right combination also to order. But yeah, one thing I can for sure know, okay, if the 4 is coming in, after that the 5 should come in. 5 should not come in before 4. Okay, one thing. In the left also, if I see, can I use the same logic? Let's say if the 2 would have came in first, then the 2 would have been here, then the 1 would have been here. But I wanted something like this, which is left and then right. But if the 2 would have come in first, then the 1 would have come in the left of that. Okay, it would have been straight. So for sure, the left ordering is also important. So basically, independently, the right ordering was important. We saw, because as soon as I slightly changed the ordering, the structure change of the right part, and which I don't want. I want the structure to look exactly identical. So for sure, if I am placing 1 should come first, and then the 2 should come, which means this left ordering is also important independently. Okay, it's important. It's important. I just look at it. But what if the 1 would have come first, or the 4 would have come first? Would have it mattered? As I spoke, okay, 4, if the 5, it would have came first, then for sure it would have become 5 and a 4. So one thing I know, okay, the 4 would come first and then the 5, right? What if I say, okay, the 1 is coming first in one case, and then the 4 is coming, or one way I say the 4 is coming first and then the 1 is coming, both having the same structure, right? As simple as that. So one thing for sure, okay, left part can come also first, right part can come also first. But if the left is coming, it needs to be ordered. Right is coming, it needs to be ordered. But these both are independent because they are left and they are right. So I can easily say, okay, next time, let's say, okay, one thing I for sure know, after 3, either 1 can come or 4 can come. After this, let's say, okay, the 3rd or the 4th number is coming in, it can come as either 2 or a 5. Okay, it can come, okay, let's say it would have come as a 2. It would have gone here. If it would have come as a 5, it would have gone here. Still, the structure is changed. Okay, you saw here, after 3, 1 and 4 can come. After 1 and 4, 2 and 5 can come. So we can see it is kind of level wise. Okay, firstly this level should come, then next the next level should come, then next the next level should come. So basically it is ordered by itself. It is ordered by itself, which means after 1, 2 should come, after 4, 5 should come, but it is not ordered. Okay, maybe the left part is coming in, maybe the right part is coming. It can happen that, okay, entirely 1 and 2 came in and then the 4 came in because 4 was on the right part. So it can come in after this also. Or it can happen that, okay, entire 4 and 5 came in and then the 1 is coming in and then the 2 is coming in. That is from this. See, we had the initial structure, we know, okay, the 3 is there. Now we tried, okay, I just want the order to be same. What can make the order different? I just try to think that way. I just had to think in the reverse way. What can make the order different? To make the order different, I just tried to place any other number. I tried to place the order, okay, let's say the 5 would have come in first, then the 4 would have been to the left of 5. So the order would have been 3, 5 and 4, which would have been different. So one thing I got to know from that, okay, the right order needs to be maintained, the left order needs to be maintained, but either left can come first or the right can come first. So basically this order is not important for me because it is independent. Left can be itself coming in the left, right can be itself coming in the right. That is how I know, okay, if I have these elements 3, so I have these 4 places to choose in. I know one thing, okay, the left part in these 4 places, 2 places are for the left part, 2 places are for the right part. I know these 2 places for the left and the 2 places for the right, which means 1 and 2 for the left and 3, 4 and 5 for the right. Now 1 and 2 for the left, it needs to come in this order, but it can come to any place, which means I can choose any 2 positions out of the 4 positions, out of these 4 positions, because I have to order. I have to place an order. So I have these 4 locations. I can place my 2 of these in any of these 4 locations, right? As you can see, 1, 2, 1, 2, 1, 1, 2, 1, 2, 1, 2, 1, 2, and lastly it would be a 1, 2, which is this example itself. Cool. So basically it's sure, okay, I can place my 1, 2 at any of these 4 locations. Cool. Out of these 4 locations, I have to choose 2 locations and place a 1, 2, and please make sure I cannot order them accordingly, which means I cannot place a 2, 1 I choose 4 out of 2 positions, which means I have got 6 positions, 6 such pairs, but it is for 1 2 itself and not 2 1. So basically, after choosing these positions for, let's say, left, and for sure, if I choose for left, ultimately for right, the remaining positions are already chosen. So if I choose the position for left, then also, you know, okay, ultimately, if I just place 1 2, the remaining whatever places are there are for right. So for sure, I choose the positions. I can choose any positions for left. Okay, it is for left, it is for left, it is for left, it is for left, it is for left. I have 4 positions. I can choose any 2 positions for left. That is 4C2, and ultimately the remaining will be for right. But in that, to order the left, it is one way. To order the right, it is again one way. That is how you build, okay, your formula. Like, now, Aryan, why you placed a 1 1 here? You said, right, I can choose anything. I can choose for left, it can come entirely as itself in this order. For right, it will come entirely as itself in this order. So it will always be 1 and 1. Then why not you place a only, you give, okay, out of the n minus 1, because see, if it is n, you have n elements, so remaining will be n minus 1 elements, and out of that, you know, okay, what are the left ones which will come, so you know what left elements to choose in, so you will just choose, okay, n minus 1, see the left ones. Why not, why you place your 1 1 here? Because right now here I said this ordering is 1. It can only be ordered in one way, 1 and 2. It's not important, it's always a 1. What if the tree is bigger? It can be ordered itself. So basically, I just said, okay, the perfect order for him is just 1. 1 after 2, it can only become in one possible way. What if I give you an example like this? If you had a 4, if you had a 5 6, it can be ordered in one way, but this, it can be ordered in 2 ways. How? It can come a 2 1 3 or a 2 3 1. So basically, this part can be ordered as 2 1 3 and also 2 3 1. That's the reason, okay, this part, left part, can ordered in 2 ways. But we know for sure, if I have these, for sure the 4 is initially fixed. See, now I'm just trying to make our example a little bigger. I know, okay, I just, from the initial example, which was small, I know, okay, it's a head. Then for the next example, I know, okay, what is the ordering like, why the left ordering needs to be important, why the right ordering needs to be important. But yeah, the left and right cannot be like, they are not much important. They can come anyways. So one thing I for sure know, okay, the left ones should come in the order. But for the left ones, I know I have these 5 locations left. Out of these 5 locations, the 3 locations will be occupied by left, and for sure the remaining two locations will be occupied by right. So I can choose any 3 locations. If these are going to left, for sure the remaining 2, it will go to right. So I can't choose those 2 because it is nothing but a 2C2 only, because out of 2 you have to choose 2 locations. That's nothing but a 1. So it is nothing but 5 out of 5, out of these 5 locations, you choose 3 locations, which is for the left. Then for the remaining 2 locations, you choose again 2, because remaining locations are 2. And then you have to choose again 2. So that's a 1. That's a reason I don't write it. But if you choose these 5 locations, now the left part needs to be ordered, but that ordering, it can be done in 2 ways. That's the reason for the left part, the ordering, it can be in 2 ways. For the right part, it is in 1 way. That is the reason that the number of ways for this will be 5C3 into 2 into 1. 5C3 to just place the left elements, but the left elements, it just means out of these 5 locations, I have just registered the 3 locations for my left. But in these 3 locations for my left, I can again reorder it to a 2 3 1. That's the reason the number of orderings, because see, I have 3 locations for left, but now in these 3 locations, earlier I was just saying, okay, it is like this, one after the another. Earlier I had 2 locations, I said, okay, 5 after 6, that's it. But now I have 3 locations with me, random 3 locations. Earlier I said, okay, it can be 2 3 1. It can also be a 2 1 3. So after choosing these 5 locations, ordering in that locations of left itself, it can be 2, and for the right ones it can be a 1. So ultimately it will be written as 5c3 into 2 into 2c2 into 1, or it is always a 1, it is always a 1, it is always a 1. So I can easily write as 5c3 into 2 into 1, which means number of ways to choose out of the remaining ways, which means if I had n locations, first is always occupied, remaining will be n minus 1. So n minus 1 c left, or for sure you can also write n minus 1 c right. Choose any and the remaining one will be gone to left or right. So if I choose n minus 1 c left, which means n minus 1, I just choose 3 locations for the left, and then to order those left ones. So let's say DFS of left, which means order the left. How many ways I can order the left? Into order the right. How many ways I can order the right? And that's nothing but the same concept being applied again on this sub part, which means this 213, again it went to a problem like this. So you saw, you had a bigger example. You choose your root, and then you find the number of ways, and then you went on down and say to your recursion, hey, just bring me the number of ways to order my left, bring me the number of ways to order my right. And then as you bring me the number of ways, I will just multiply all of them and just multiply again with n minus 1 c left, which means the number of remaining ones. If I had this entire total as n, so remaining ones are n minus 1, so n minus 1 c left, which means the left count. And that is how the recursion and combinatorics are applied so beautifully in this problem, that this was an amazing problem. So now ultimately, you know one thing, you will just follow a simple recursion, simple as you do as in a simple tree traversal, going on left, going on right. Just while coming back, bring in the answer as n minus, if you had n elements in your array, n minus 1 c. Okay, what all elements are the left ones, and how to know what are the left ones? Simply, if it is the root, the left ones are always smaller than the root. Okay, you will get two elements which are left, remaining 2 will be right. Okay, whatsoever elements are bigger are the right ones. So okay, now you know, out of the n minus 1, I have 2 left elements from left recursion, which means as I'm coming in, see, as I come in up at the recursion tree, I just have the information of left, I have the information of right. As I'm coming in, I know, okay, what is the information of left? I have the DFS, and see, while doing the recursion, please make sure that you assume one thing, you will get the data from recursion itself. So it is nothing but the order for left, which means the DFS of left, and it is nothing but the DFS of right. And that is, it is nothing but the left, the number of elements in the left. And that is how it will become by recursion. You will just assume, and when you have computed for your left and right, you're coming to root, because in a tree it's nothing but left, right, left, right, left, right. It's left, right, root, you coming in, you got the information. Now again, it's left, right, you coming in, you got the information. So as you're coming in, you have the information of left and right. Just do a multiplication with n minus 1 c left, and then return. That will be information for your new root, and that root can act as a next left or right. That is how you can simply do it. So ultimately, you have your n numbers, one number is always fixed, you have some left numbers, you have some right numbers, and how you know the left and right? If it is smaller than the root, it's in left, it is bigger, it is in the right. So you have your left, you have your right, you have your n minus 1 numbers, so n minus 1 c left, or you can also do a n minus 1 c right. Both are same, because you can choose any of n minus 1. You have n minus 1 locations, you can choose left or right to place in. The remaining locations will be automatically assigned to, if you choose left, to remaining places will be assigned to right. If you choose a right, remaining places will be assigned to a left. And that's how you know, okay, you have choose left locations separated out of these n minus 1 locations. Out of these n minus 1 locations, you have choose some left locations for your left guy, and then to order in that, you will bring in the ways for left. To order for the right, you will bring in the ways for right by a simple recursion, and that will bring in your answer to the top, and that will be your answer for the root. Cool. Let's quickly jump onto the code. It was pretty easy. Just going over examples and finding the one thing from that example itself, which can help you to actually grab the entire logic. And just in these pattern problems, just try to make the pattern a slight bigger, and from that slight bigger pattern, you will just automatically get the answer itself. So always make sure in these kind of problems, start from the examples itself. From examples, grab an approach, pattern, intuition, everything, whatever you want for the problem, and then from that, just try to make the pattern a little bigger to actually know what you applied for a smaller pattern, is it actually applicable on the bigger pattern also. And that's how you solve these kind of problems. Cool. Let's quickly jump onto the code. But before that, you will see entirely one thing. As I showed you, it's a maths problem. So I'll teach a quick maths in that also. For that, you will just have to know, okay, what's an NCR? See, when I say NCR, it's just choosing R locations out of N locations. That's it. That's legit it. And for that, if you had no idea, okay, what's an NCR, what all that stuff he means and all that stuff, just quick two formulas you have to remember always. NCR is nothing but n factorial upon r factorial into n minus r factorial. To compute NCR, which means choosing, and when I say NCR, it just means, okay, if you have n locations, you have to choose r locations out of these n locations. Just choose blindly. Okay, these allocations are there, and that is how what you mean by NCR, choosing R locations out of n total locations. Cool. To compute this NCR in computer science, you have two formulas, n factorial upon r factorial into n minus r factorial, which means when I say two formulas, there are many, but how we compute it, okay, we know how to find a factorial. It's nothing but n into n minus 1 into n minus 2 and so on and so forth. So multiplication, it can be done in computer science, so that I can do for sure. But you will see that it's upon r factorial, and for sure, if you remember one thing, you have to do entirely modulo n, modulo your mod number, which is some mod number. So it needs to be a mod of something. So that's the reason you will just write, okay, inverse of r factorial into inverse of n minus r factorial. In your competitive exam, in your actual competitive exams, which means when you solve the CP problem, then it's good to actually use this implementation of NCR, which means n factorial into inverse of r factorial into inverse of n minus r factorial. But if you're solving in an interview, how will you write the inverse code? It may be a reason it may be a chance that you might not remember the inverse code, how to write the inverse code. Also, although it's pretty easy, but yeah, it might be a chance that people who are not much familiar with number theory and stuff, they might not be able to write the inverse code. But if you don't, then here's a quick another formula for NCR, which is n minus 1 CR minus 1 plus n minus 1 CR. And I have shown the proof also. N minus 1 CR minus 1, it can be written as n minus 1 factorial upon r minus 1 factorial, which means n minus 1 factorial upon r minus 1 factorial upon n minus 1 minus r plus 1, which means 1 will cancel, which will become a n minus r. Cool. Now, I have this again written as n minus 1 factorial upon r factorial upon n minus r minus 1 factorial. I will just know I want to make something like this, which is nothing but n factorial upon r factorial upon n minus r factorial. So I will quickly have to grab something common out. I know I have to make it r factorial, so I just multiplied r to get r factorial. I got r factorial from r into r minus 1. From this n minus r factorial, I want to grab something out common. I know here it is r minus n minus r minus 1. So I just made it as n minus r into n minus r minus 1 factorial. I just now grabbed r factorial common, n minus 1 factorial common, n minus r minus 1 factorial common, and then I will just grab these three things out. Remaining will be r thing, which is this. Remaining will be n minus r, which is this, and plus 1, because entirely it is gone, so it is plus 1. As I do addition, it will be r cancelled, and will come in and club with n minus 1, which will make it n factorial. R factorial will remain as it is. N minus r will club in with n minus r minus 1, which will make it n minus r factorial. That's the reason you will get a NCR. That's the reason. Please remember these two formulas. NCR is nothing but n factorial upon r factorial and n minus r factorial. Can be solved via inverse also, inverse of factorials. And also, if you don't want to go, you can go via this way of finding NCR. Again, you will ask me, Aryan, here also we have to again compute n minus 1 c r minus 1 factorial? No, you don't have to. You can simply go and apply a loop, start from a smaller value of ncr and keep on, because see, you are seeing that it is nothing but for using your n, I am using a n minus 1. So for sure, if I want to compute for I am using I minus 1 values. And I can start from very small I values, and then I can just keep on bringing my I bigger values from the I smaller values. Here also R minus 1 and R. So for sure, if I have a J value, so just that, okay, I primarily is important. J I can start from 0 and itself like that, so that I can get, okay, higher values from the smaller values. And that is how I just said, okay, it's a DP problem that you just pre-compute some part, although it's not exactly a DP, but yeah, it was primarily combinatorics plus recursion. It's cool. Now you just remember these two things. Why? It will take n square time, which means it will take n square time to actually get all your NCR pairs. It will take n log n time. That's the reason I just said that in a competitive programming, which means if you are doing competitive programming and stuff, do it like this. But in an interview, you have to explain and stuff. Maybe interviewer might not know about inverse. Many interviews don't know, so it's good to go by this way, because no rest the compression will remain same. So yeah, that's, now let's quickly jump on to the code itself. One thing for sure, it is my main function. I just have this mod which will actually be used to do a modulo at every step. When I say, even if I add a plus b, I need to do a mod m. I do a multiplication a into b, I need to do a mod m. Anything I do, I need to do a mod m. One thing for sure, here I just pre-computed my what? My NCR by just, when I say pre-computation, I just need to apply a for loop from up till n, right? And to get a NCR. And for sure, if you don't know, NCR, n is always greater than equal to r, because you need to choose r objects out of n, right? So n will always be less than or equal to r. That's the reason. R is always less than equal to n, right? That's the reason you will have a pre-computation, let's say a name as table or anything whatsoever you want pre-compute, anything. It will just compute for all nr pairs what is the value, and by using this formula ncr, n minus 1 cr minus 1, n minus 1 cr, ncr I cj, I minus 1 cj minus 1 plus I minus 1 cj. And just simply applying a 2 for loops to get that answer for ICJ. Now I have the ICJ for all the pairs required, which means up till n is nothing but nums. So I have got all the NCR pairs whatsoever it could have been. Now I will just actually call my DFS function, which will actually find the answer for this nums, how many reordering can be possible. Now, as soon as I get the answers, this function will give me all the possible ways, right? All the possible ways to get the answer. But you remember one thing, in the question itself, one way is already given. So if I in total get the 6 ways, one way is already given. So give me 6 minus 1, which is 5 ways. So ultimately I will get all the ways out. I'll get all the ways out from this function of DFS. It will give me all the ways, which is, let's say, all 6 ways, but I need to return one way is already in the question itself. So return the remaining way. Answer minus 1. Cool. Still, I did a modulo because it's important. It's important to do a modulo at every step. Now, cool. Now let's go to this function of DFS. Now in this DFS functions, what is happening? Firstly, I just know one thing. If I have only, see, whenever you write a DFS recursive functions, just make sure what was your main condition, what is your recursive condition, and what's your base condition. Now, as soon as I write, okay, what's the base condition like? Just look at a very small example. If there had been just 2 elements, if there had been just 1 element, if there had been no element, or if there had been 3 elements. If there had been 3 elements, okay, I still could see some ordering possible. You saw. So for sure, the 3 was not a very small example. Let's look at if I had only 2 ways, only 2 elements. If I had only 2 elements, let's say 4 and 5. So for sure, I know 4 will come and then 5 will come because 4 is fixed as root. So it needs to come, and if it needs to come at this location, then the next location will always be for the next number. So for sure, this is fixed. This can only come at last location also because the location itself 2. So for sure, if the elements are 2, number of ways are 1. That's the reason. How you saw, okay, what is the base case? Just think of any small cases. Either can be no case, one case, either it can be no, either it can be a no case, one case, two case, and just try to bring, okay, what is the smallest case you can bring? Cool. Now, you can also put as n equal to 1 also. That will also work. Just have to modify a bit in the main code, but yeah, that also will work. Now, you know, okay, it is a base case. As soon as you go to the base case, firstly, you know one thing for sure. You have to go and ask your recursion, okay, hey bro, please bring me the ordering for the left and the ordering for the right. What is the number of ordering for the left? What is the number of ordering for the right? For that, your recursion will ask you, hey, what is the elements of left and what is the element of right? Because from that elements itself, okay, if you just say, okay, this is the element right now I can tell you, okay, 1 is coming as first. So for sure, 1 needs to come as first, and then I'll just let you know what is the ordering like. So this ordering is also important of left and right. As you saw here in this example itself, if this would have been a smaller part, as I showed you, where is going? Yeah, if it would have been a smaller part, so one thing for sure, in the ordering, 2 would have come in first, and then 1 and 3, then 3 and 1. So for sure, left element needs to be there, but also I need to know what is the ordering of left element, because in that I need to know, okay, 2 will always come first and then the other elements will come in. So I will just I need to grab the left element number also and then the elements also, because I need to know what is the first element like. So I will just quickly go and grab what are all the left elements in my current nums whatsoever I'm having, and what are the right elements. Now I have got the left and right elements. I'll quickly go and ask recursion, hey recursion, please give me out what is the number of ways to order left, what is the number of ways to order right, what is the result for left, what is the result for right. Now as the recursion gave me, and I just blindly assume it will give me, I assumed it will give me. As soon as it give me, I have the left answer, which means the number of ways for left. I have the number of ways for right. I just need to do a quick one thing, right? You remember one thing which we have to do? We have to only simply do a n-1c left or n-1c right, whatever you want to do. So n-1c left I did, n-1c left, n-1c left. It is left result, it is right result, and n-1c left, and that I can quickly return to my actual function. So assuming it will give me an answer, please mark my words, it is how recursion is being thought of. I firstly know, okay, what is the base case? In that I thought. Then for the recursive case, I know what the recursion needs to get. It needs to have an array, because for that it needs to grab the first element, all that stuff. So it needs to have an array. Okay, recursion input, which means the left and right input, I know, okay, it is input. I assumed it will give me the required output, and then by assuming, okay, left and right are giving me the required output, I can just easily go and say, okay, if my left and right are giving me the output, I will give you this output, I will give you this output, return that output, and from that I can actually solve this via recursion. So that's the reason I just showed you how to think of recursion also, because I've seen many people just get confused in recursion. How to think? मुझसे होता ही recursion? ठीक है, नहीं होता. Just assume left and right will return. Just assume. You have to find the base cases very small possible, and also what needs to pass in your recursion left and right. What is the input they will take? What is the input they will require? And that's the reason how we'll just get, okay, left and right will get the input, and for sure at every step just simply do a modulo. When I say modulo, every step, multiplication, step. Here also I did a modulo, then again I did a modulo. So do a modulo at every step, and that's how you will just simply issue your answer. Complexity will be nothing but here O of n square. Here for that one element, for this one root, I'm going on to the entire array itself to know what is the left and the right. So for one element, I'm going on to n other elements. Then the next element, I'll again go to n-1 elements, then n-2, then n-3, so on and so forth. Although it is bifurcated, which means n, then you have some left. But if it is a strictly, like, you know, linear kind of, which is 1, 2, 3, 4, 5, 6, so it can go to n square. So yeah, that will go to again n square, your DFS functions, your main functions. It can actually, if you're doing computer programming, so it can go to n log n. if you just do a pre-computation. But yeah, that also is not much required here because ultimately the constraints are up till 1000, n is less than 1000, so that can work both ways. Ultimately it will be n square only because of this DFS function call, which you're actually calling in for a particular root, going on to all the left and the right childs to actually know, okay, what are the left and what are the right childs. And that's how you can simply get your answer. Time is O of n square, which means for NCR pre-computation and for the DFS calls, and space also of n square because of the NCR space. And that's how you will simply solve it. Code is down below. I hope that you guys got the proper intuition of how you think of these tree problems and how to find the pattern where the math problem is being applied. Math is nothing but finding a pattern out and applying the formula for that pattern. Finding a pattern, start from a smaller pattern, start from a smaller problem, make it bigger, and try at every step, try to figure out, okay, what I can add in my pattern. For smaller, we saw, okay, it is a root, and then, okay, if it is a left and a right, how the patterns of left and right. If it is a left and right, if we have a pattern, if it is a strictly a pattern, or we can have another ordering inside that left or right also. That's how you simply grow on in your pattern problem. And then when you know the pattern, to solve it via the recursion, you just assume three things. Okay, you base case, you will find very small. A recursion, you will just assume left and right will bring the answer. Just have to make sure you are passing in the correct input to your recursion of left and right. And then while returning, which means while actually computing your answer, you assume you have the answer for left, you assume you have the answer for right. Just add your particular contribution in your left and right and return the answer. And that's how your recursion will be built automatically. Cool. I hope that you guys liked it. I know the video has gone a bit long, but I want to quickly go deep inside the math, combinatorics, and recursion. That's all. Pattern, combinatorics, and recursion. Cool. That's all. See you in the next video. Bye.